which was great.
Yeah, which is the sort of thing. So we're gonna start pretty quick here, but it's the sort of thing that I want to, we'll ask the. I'm gonna put out a survey later, everyone, and be like worth 1% or something if you fill it out, because a lot of you've been wanting that like 1% opportunity to do something there. So we're just gonna do it as a survey though, not like a concept questions that we had at the beginning of the course. So we'll do it as a survey, and then yeah, just think about any. It won't be anonymous, like course evaluations. That's what that'll be for. It won't be anonymous, but it's an opportunity for you to do things like tell me, did you use the digital textbook a lot, or did you mainly use the PDF, or were there any spots where you'd have preferred more videos or less videos, or whatever the case was. But so you'll get a chance to answer that survey later, and we'll give everyone 1% for answering it. Okay. All right, so let's get started. Okay, actually, you know what? This week I kind of wanted to, because again, I have a feeling that people are kind of starting to burn out. And so I'm going to break my own rule, because normally I wouldn't do any kind of, we just kind of jump into questions. This week, I do want to start us off because we're starting multivariate calculus. And I do actually kind of want to just talk about procedurally how we do things very, very quickly, and then we'll start doing questions. Multivariate calculus for us is simultaneously going to be, some people think of it as being pretty difficult, and I think some people also think it's pretty easy. So it's very hit or miss. Some people find it straightforward and some people don't. And the reason for that is, unlike most of the rest of the course, I can't ask you a lot of conceptual questions about this part. This part is thrown in here because you use this sort of stuff as you go on and do more advanced economics or whatever the case may be. So you have to learn this stuff at some point. But I can't teach it to you well because there are literally entire courses dedicated to this material that we're going to spend 3 weeks on. So it basically comes down to the fact where I'm basically just trying to get you to learn the tools, right? So what that means is none of us can go conceptually too deep into this, and it's more of learning the tools and the computational algorithms. And for many of you, that's great, right? Like you maybe don't like the concept part, but you like the computational portion. And so if you're one of those people, this might seem easier. On the other hand, simply by virtue of the fact that it's multivariable stuff, it gets a little bit harder. Okay, so just something to think about and be aware of. Okay, now first of all, I know that some people think that, if you see a y is always equal to f of x. That's not true. Okay, so first thing, you have multivariable functions. This is a little bit writing in a weird angle. So we've got multivariable functions. Okay, we might write something like f of xy for this. Right, and I made you play with some of these. Maybe I give you something like x squared plus y cubed. And right, y here has nothing to do with x, right? Nothing whatsoever. It's just if you plug in number 7, 3, something like that, that means that where you see an x, you're going to put a 7, and where you see a y, you're going to put a 3. And so we would evaluate that as 7 squared plus 3 cubed, and whatever, 49 plus 27 is what, 76, whatever number it is. Okay? So y does not mean f of x. And instead of calling it x and y, we might call it x1 and x2. That's a thing that we do as well. Okay, so I don't want you to be thrown off by that. So we could do something like that, especially when there's lots of variables and we don't know, how many of them we're going to need, or we're going to run out of letters really quick. We might just call them variable x1 and variable x2. Okay, now if you've done the reading, kind of the critical part here is in terms of partial derivatives. So let's say I give you a function of, let's start with just x and y right now. In fact, let's just use the same function we had up here, x squared plus y cubed. So what we can do is we can talk about the partial derivative of f with respect to x. Okay, and when we do this, we use this weird thing that looks almost like a curly D. It almost looks like a 2 for me, but it's a curly D. And what this means is take the derivative with respect to x, treating y as a constant, or let's say treating everything else as a constant. as constant. Okay, so you tell me, I've got this function x squared plus y cubed, and I want to compute df dx, right? So I want to differentiate it in the x variable, treating y as a constant. What would I get? Okay, and then if you know the answer to that, you can do df dy as well. 2x, beautiful, perfect, okay. And then what's df? And so die, right? We, instead of saying df dx, we would say dif dx. So what's df dy in that case? 3y squared, beautiful, perfect. Let me put the xy in here. Right? Okay, so in this case, right over here, we treated the y as a constant. So it's almost as if I'd written x squared plus 7 cubed or something. You know that even if you don't evaluate the 7 cubed, it's a constant. When you differentiate it, it becomes 0. Same thing when I differentiate with respect to y, that x squared term is a constant, and so it dies as well, right? It just vanishes. So is everyone okay with partial derivatives? Does anyone want to ask any questions about how these things are computed? Right, like here, maybe let me do, let's do another example really, really quickly. Dy y e to the xy. Anyone know what that one is? So you got e to the xy, and you take a y derivative of it. What is it? Perfect, yeah. X e to the xy. Okay, so if anyone is not okay with that, you need to flag me down and say something now so that we can go over it, because you need to know how to do these things for today's questions. And if there's any kind of anything there that's messing you up and keeping you from being able to do it, then you've got to let me know now so we can go over it in more detail. Otherwise, I'm going to assume that everyone's okay with this. Yeah, it might be a bit of practice. Right. Again, here, you know what I sometimes say? Again, kind of pretend. I've had a lot of success with this in just showing it to some students. But if I'm differentiating with respect to y, then x is a constant. And so what I'll actually do is I'll have students, replace it with a constant. Right. And now students can do this, no problem. They're like, oh, yeah, OK, the 2 comes down, right, because I use the chain rule, and I get 2e to the 2y. And I'd say, OK, well, instead of leaving that as a 2 there, right, replace it everywhere with an x. And this isn't how you should actually do it. I'm just trying to illustrate how the role of the constant is coming into the actual differentiation, right? But if it helps, actually try replacing it with a constant at first and then seeing how that works when you actually differentiate it. And I've found that some students really benefit from that when they're kind of confused. In fact, this is a good one. Well, let's do one more set and we'll start with the questions. So dy x of x to the power of y. All right, let's try that one. What's the derivative of x to the power of y with respect to x? Okay, you're just pretending y is a constant. Yes. Yeah, perfect. Beautiful. Both of you. Excellent. So you get y x to the y minus 1, right? That's like your product rule, right? It's like if I'd asked you, what is the derivative of x squared? The x is in the base, the constant is in the numerator, so you would use the power rule, right? Okay, now what if I go the other way, though? And what if I ask you to differentiate this with respect to y? What would you get? It's not too bad, right? Don't overthink it. Like, pretend that x is a constant. Close, Kevin, but not quite. You're missing something there. Yeah, perfect, exactly. So ln x to the y, right? And how do we see that? Well, let's let x be a constant. Maybe let's just call it 2. How do we differentiate? 2 to the y. Let's use y's here. How do I differentiate it if I've got a constant in the base and the variables in the exponent? oh, well, that's ln 2 to the y, right? And same thing, you just kind of think about it. Oh, yeah, okay, so x to the y, that's ln x to the y, like that, right? And that's what I'm saying. Like, it can help to think about, this isn't actually, again, I want to emphasize that you shouldn't differentiate 2 to the y, and everywhere you see a 2, put an x. That's a bad idea, because 2's might show up in other ways that it doesn't work if you replace them by an x. But just so you can kind of see and remember what rules you want to use, think about it, and by actually putting a constant in there and be like, oh yeah, okay, this one is like an exponent, and so I'm going to do something with like differentiating 2 to the x or e to the x or 3 to the x or something like that. Okay, so that can help. Okay, so let's start off here. Let me give you a poll question version of this now. All right. All right, so we've got this function up here. And I want you, remember, this is shorthand for the derivative with respect to x. Okay, that's a shorthand notation for that. So if I give you that and you want to differentiate this function with respect to x, what number do you get? What answer? Let me take a look, Sarah. 11.1. Yeah, you know what? You're right. It should be 11.1, 11.2, and 11.3 are all in there. Let me see if I can't change that. There we go. Thank you, Sarah. Actually, is that, oops, sorry, wrong thing. Yes. Okay, so we're doing pretty well. We're at 52% so far. Let's do another 30 seconds and we'll tie it up. Squared over 1 minus y plus y. Okay. All righty, 73%, not bad. We're going to end the poll. Let's share the results. And there we go. So we got 62% on A. A is absolutely the correct answer. If you answered B, you're very close. But don't forget that y here is a constant, right? So that's actually going to hang around. C is actually the answer if we wanted the Z derivative, and then D doesn't give us anything. So let's see this. Let's take this up and see why this is true. All right. So here's our function, right? Z squared 1 minus y plus y ln x. And we want to compute di f di x, right? That's what di sub x f means. Those are the same thing. Okay, so when I look at this, note that this thing here has no x's in it. Contains no x's, right? And so is a constant. Right? That means that when I differentiate it, it's just going to give me 0. So when I compute di f di x, that's going to give me di x z squared 1 minus y. That whole thing right there, that's going to be a big old 0 because it has no x's in it. And then I'm going to compute the derivative with respect to y ln x. Okay, now however you choose to do this, if you wanted to, you could say, okay, listen, y there is a constant, so I could actually just pull it out in front of the derivative. You can leave it in if you want, but this I think maybe makes it a little bit more clear. Because it's a constant with respect to the derivative that I'm taking, I can actually just take it out of the derivative, right? We know we're allowed to do that. If this were the derivative of 2 ln x, I could take the 2 out and I could put it on the other side. So same sort of thing. And then we all know how to differentiate ln x. We're masters of that by now. So we get y times 1 over x. And if we just combine that, that gives us y over x, right? And that was answer A. Okay, so if it were y to the x ln x, what would the derivative be? Okay, sure. Yeah, good question. Okay, so you're saying, let me make sure I got the function right. So let's just take a look at, maybe let me call it something else, g x y z. And you're saying y to the x ln x like that? Okay, yeah, great question. Okay, so let's do the derivative with respect to x of this function. So y to the x ln x. Oh yeah, this is going to be good. Okay, so I've got 2 functions of x here, so I'm going to have to use the product rule, right? So I'm going to do the derivative of the y to the x term times ln x plus, so derivative of the first times the second plus the derivative of the second times the first, right? Now, this one we actually did above, right? So this one we actually did above. So that's going to be ln x, ln y, y to the x, ln x plus y to the x times 1 over x, right? And you could stop there if you want, or you could be like ln x, ln y, y to the x. You know, there's some simplification you could do here. I mean, I wouldn't go much further than that, but does that make sense? How do I get the derivative of y to the x? Sure. So again, it's like, so the derivative of y to the x, it's the same as, you know, again, thinking about this as the derivative. Remember, y is a constant. So if I put like a constant in that place, how would I have done this? Oh, it's ln of 7 times 7 to the x, right? And so in this case, if I want to compute the derivative of y to the x, realizing that y here is the constant, I would get the same sort of thing, only instead of the 7 now, right, I've got that constant y everywhere. Does that make sense? Okay, cool. So yeah, so absolutely, right? You might have to use product rule, you might have to use chain rule. And this is what I'm saying, like, you all know how to do this, but there's a certain conceptual barrier that you have to get past where there are all these variables hanging around and you have to keep track of which one you're treating as constant. So this is definitely the sort of thing where you need to do a little bit of practice and get comfortable with being like, okay, I'm differentiating with respect to x now, so the y's are constant. And if they're constant, how do I recognize what rule to use? And that's why I like to do this thing where, you know, I say if you can't see what rule to use, don't just guess. try and actually, if you're differentiating with respect to x, replace everything else with actual numbers, and that might give you an idea of what sort of derivative you would do, and it might make your life a little bit easier, right? So you give that a shot and see, and maybe that'll help you out a bit, right? And again, this is definitely the sort of thing like a lot of the computer algebra systems can do. So don't hesitate to, make your own question and then just see if you can double check your answer by Wolfram Alpha or Simulab or whatever. Okay, so let's try this one. Okay, and so for those of you who maybe don't remember, the gradient is the vector that is where the first component is the x derivative, the second component is the y derivative, the third component is the z derivative, and so on. In this case, we only have two variables, so it's going to be just a 1/2 vector of the x derivative and the y derivative. And yeah, there's something else to be said here, which is for those of you who hated linear algebra, unfortunately, it's coming back because you need linear algebra to do multilinear calculus or multivariable calculus. And all the things, determinants, eigenvalues, it's all coming back. Human, thank you. I didn't realize that before, but very nice. The triangle, so the triangle is the gradient vector you can choose. So the triangle says take the vector of partial derivatives of all the possible partial derivatives. Okay, so it's, I don't want to switch screens right now, but actually, you know what? I might be able to find it in the digital book and then just show you. Where is it? Yeah, here it is. Okay. All right, so I'm going to throw this onto the shared screen here. Hopefully this, okay, so it's going to make the question zoom out a bit. So it's right here. All right, so this thing, which is called a nabla or a del or grad, it's got a bunch of names. So it is the row vector that is the x partial, the y partial, ... through the last partial, right? So you compute all the partial derivatives and you put them in a big long row vector. Okay, so that's how you do it. Oops, and let me just fix this. Does that make sense, Yinchi? Does that help? Okay, perfect. Yeah, so it's saying compute the x derivative and then compute the y derivative and put them in a vector. No problem. And many of you are probably starting to see that, like, in these sorts of questions, if you can compute one of the components correctly, you know which vector it is because it's multiple choice, right? All right, so we are at 45%, which is pretty solid. Let's do 40 more seconds. That'll take us to the 5-minute mark, and then we'll take it up. So get your votes in. Do the second component doesn't help you different? Yes, that's true. In this case, you can see all the second components are x squared e to the xy, so it doesn't help you. So if you observe that, which you're like, okay, actually all I need to do is compute the x derivative and I can figure out which one it is, right? So it saves you a little bit of time if you observe that, but yeah, you're absolutely correct. But again, we just want to get a little bit of practice, you know, looking at these variables and being able to be like, okay, when I'm differentiating this, these are constant. So it's, oh yeah, so you did them. Nice. Yeah. And you know, something to keep in mind as well, which is, I think it's very easy for students to be like, you know, absolutely. It's very easy to look at these and be like, why do we care? That's great. Yeah, Maya, I love to hear that. Why do we care about this? But of course, you know, most of life occurs in multiple dimensions, right? Whether it has multiple variables. I think I gave you the same spiel when we were talking about linear algebra, right? But most of life has multiple dimensions, multiple variables, whatever the case may be. So the reality is that our first year calculus was really just to like, or a single variable calculus is just to get us ready to do multivariable calculus, because it turns out multivariable calculus is actually where most of real life happens, right? Okay, so yeah, we've kind of got a nice consensus on D, and D is absolutely the correct answer. Very good. So let's see why. Okay, so what we're going to do, I've written here just to expand this and help remind us what the gradient vector is. Okay, so the gradient is the x component and then the y component, right? And we put them in a vector, and that's a row vector. In this class, it's not going to matter too much whether it's a row vector or a column vector, but strictly speaking, the gradient is a row vector. Okay, so we just need, all we need to do is compute both of these derivatives. So let's compute the, you know what, let's compute the y derivative first, just because we know it doesn't matter, but let's practice doing it. So let's start with computing di g di y. Okay, just because we know what the answer should be, right? We know it should be x squared e to the xy. So that's going to be di y of x e to the xy. And again, we're differentiating with respect to y here. So I'm going to pull that x out. Okay, I just don't want to have to worry about it. I don't want it to get in the way. I don't want us to accidentally, you know, try and apply the product rule to it or something like that. So I'm just going to get it out of there. And then once again, right, so we're differentiating with respect to y, and we did something like this at the very beginning of the lecture. So that x constant term is just going to pop out, right? X e to the xy, like that. Right? It's same thing. If you were differentiating e to the 10y, you would have gotten 10e to the 10y, right? So that's what's going on there. And so that's going to give us our x squared e to the xy, like that. Okay? But of course, we already knew that because all the multiple choice has that. So now let's compute the more interesting one, the one that's actually going to differentiate the answers. So we need to now compute the x derivative of x e to the xy. Now this time I can't pull the x out, right? I'm differentiating with respect to x. It's not a constant anymore. So I have to product rule it. And, you know, again, if you practice this, you will get to the point where you can do it in your head, and you might not be there yet, and that's okay. But we get to here, right? And I haven't done anything. All I've done is like applied the product rule, derivative of the first times the second plus derivative of the second times the first. And okay, so some of these we know, right? This first derivative is pretty easy. This is just 1, right? The derivative of x with respect to x is just 1. And then when I differentiate e to the xy with respect to x, it's exactly the same sort of thing that happened in the line above, except now I've changed which one is the constant, right? So I'm going to get y e to the xy, right? And just compare these two square brackets here, right? This bracket up top was the y derivative. This bracket down here is the x derivative. Di x e to the xy. Notice that you get very similar answers, except, you know, the roles of x and y have changed. And so after all of that, you just get e to the xy plus xy e dxy. And you can factor out an x to the y if you want. It's not a big deal. But either way, that gives you d. Right? I tried to do it in my head, but it's hard to separate terms. Yeah, that could be. And Xupeng, I'm sure you'll get there when, if you do enough practice, right? But I would say, especially now as all of you are kind of starting out, and probably, I know that for sure some of you have done calculus before, and maybe the product rule was nothing new. It's something you'd seen and you felt like pros. For this one though, even if you're really good with the product rule, it's really easy to make mistakes because there's so many variables flying around. And it's probably worthwhile just to slow down at first until you get used to it. Because again, this isn't the sort of thing that you want to make a mistake on, right? Like you can imagine that I mentioned that the computations in this section can be quite large and quite nasty. And this is the sort of thing, if you make a silly mistake here, it's probably going to screw up your whole question, right? So you just want to go slow, make sure you get the right answer. And again, maybe double check with Wolfram Alpha if it's a test or something. But eventually, it comes with practice, but you can absolutely do this in your head. Eventually, you'll be able to get there. Okay. All right. Let's try another. I like this one. So you're going to see something cool happen here. All right. So depending on how far you've read ahead, you know what it is that we're trying to do here. Okay. So there's a sense in which this thing, the gradient of f, is the correct notion of a derivative for us, right? Because we can't differentiate multivariable functions. We can only compute their partial derivatives, right? And it's even in the name, partial derivative. It's not a full derivative, it's a partial derivative. So for us, the gradient is somehow the total derivative, right? And I've taken all the partials and put them together, and that gives me the whole picture. And if I'm trying to compute where the derivative is equal to 0, well, what do we call those things in one variable calculus? What do we call something that makes the derivative equal to 0? They have special names, right? Tangent line. I mean, the derivative gives you the slope of the tangent line, but yeah, exactly. Critical points, right? Critical points are where the derivative is equal to 0. Exactly. And we know that critical points are useful, for example, because they help us find maxes and mins. And you can imagine a very important application of what we're going to want to eventually do is maxes and mins, right? So what we want to do now is I'm giving you a function, and this function has been perfectly designed so that it's relatively easy to solve. But let's find the values of x and y, which make this gradient equal to the 0 vector. What you're going to find is it's significantly worse than one dimension. I think I remember the answer to this one. Can I quickly zoom out inside for a solution? Sure. Yeah. Let me take up. Like I said, I'll take up the solutions after this, and remind me to do it in case I forget. There's a cool thing here too, everyone. So again, some of you might be wondering, like, how is this applied? This year, we've kind of I've been skipping a lot of the applications, and I don't know exactly how y'all feel about that. I'll tell you, when I was a student, I mean, I became a pure mathematician, but when I was a student, I hated seeing the applications. Like, oftentimes the applications are very contrived, and they didn't feel like they were actually useful. If when I was given an application that actually was an application, that was super cool, and I love that. But of course, in first and second years, often we're kind of building up the machinery in order to be able to do the cool real applications later. So anyway, there is a part of the book that is written here that does have some applications to economics and finance. And if you're interested in checking them out, you absolutely can. We'll talk about things like complementary and competitive products, which I think is a cool but relatively simple application of partial derivatives. There's things you can do. I don't even remember them all, but you can go check them out. Obviously, there's marginal blah, right? Because marginal more or less just means derivative. But if you guys want to go check that out, they are written up. I did type them all up and put them in the book. But we're not going to worry about them in terms of testing you on them and stuff like that. So we're not going to worry about making you do any readings on them or creating any questions. Okay. So if you're worried about whether these things actually have applications, the answer is yes, but we're not going to worry about them. I'm going to let your econ management profs, whatever, worry about that. Okay. I'm going to focus more on teaching you the underlying mathematics. Okay. But they're, like I said, they're in the book if you want to go check them out. It's all right. It happens. I remember back. Do you all remember back in fall when like every poll question we had, we'd get like 7 people who were like, "Oh, I clicked the wrong one." Those were the days, eh? It seems like forever ago, actually. Like it was only, within like the last 6 months, but man, did it? Yeah, exactly. Does it not feel like an eternity ago, though? Man. Right, Abdul Rahman. Yeah. You can do more than that. Yeah, I'm not 100% certain how you got to that one, but you may just want to wait then until we take it up, and maybe it'll be clearer. Chifeng, no, my recollection is not that is it. That's not it. I don't think. I could be wrong, but I don't recall that being it. Nope. Yes. Okay. Well, I mean, yeah, if you just put them all, eventually, yes, one of them will be right. All right. Let's say 30 seconds. We'll wrap this up and I'll take it up. And I'll show you the reason why multivariable calculus is so much harder. And for those of you who hated linear algebra, why you're going to be desperately wishing that we were still doing linear algebra. I do think it is fun. I agree. But there's no doubt that this stuff is a little bit harder, right? Maybe it's harder by virtue of the fact that it's fun because it is hard. Okay, so our consensus is on B. B is, to my recollection, the correct answer. So let's take this up and let's see if I can get B as well. That'll be the real challenge. Zoom, come on. What are you doing? Yeah, tedious, maybe, sure. Okay, so I've got this function, which is just a big old polynomial, and I want to figure out where its gradient is equal to 0. So first thing I have to do, obviously, find the gradient. All right, so here's our answer. So we'll find the gradient. So we're going to take the x derivative and the y derivative. Di f di x, di f di y, like that. Okay, and this one's not too bad to do, so I'm going to go through it pretty quickly, but again, kind of, yell out if something doesn't make sense. 4y cubed minus 4x. Okay, did we all get that? Again, you have to double check me, just make sure I did my math correct. Okay, that looks good. So what you see is we get two equations and two unknowns. All right, so 4x minus 4y has to be equal to 0, and 4y cubed minus 4x is equal to 0. And let me just get rid of the 4's because we don't need them. So we get x cubed minus y is equal to 0, and y cubed minus x is equal to 0. Okay, so, and hopefully you can appreciate what I was trying to do with the numeracy question here. This is a nonlinear system of two equations and two unknowns, and we have to solve it, right? We have to solve it simultaneously and find the values of x and y which solve this. It's not linear, right? So we can't use a matrix or anything to help us. We're just going to have to, basically figure it out by using cases and so on and so forth. So what I'm going to do is I'm going to number these. Maybe let me call this 1. Let me call this 2. So write 1. As y is equal to x cubed, right? So I'm just going to put the y on the other side and sub into 2. To get, so what is this going to give me? I'm going to get x cubed. Oh, here, 0 is y cubed minus x, but y is equal to x cubed, so I'm going to get x cubed all cubed minus x. So that's x to the 9 minus x. It's x times x to the 8 minus 1. Ugh, gross, right? Okay, but we can keep going. So that's going to give me x times what? X squared minus 1 times x squared plus 1 times x to the 4 plus 1. You know what? Maybe that's too quick. Let me break it down into smaller pieces. X to the 4 minus 1. X to the 4 plus 1, right? Difference of squares. How I got 4y and 4x. Okay, sure. So, okay, so the question was, how did I get these things? And so here I've got the x derivative of, let me just get the function. So x to the 4 plus y to the 4 minus 4xy plus 1. Okay, so certainly the x derivative is 4x cubed plus 0. And the one term goes away. Whoa, that guy was loud. Okay, so here now I get minus 4 times the derivative of xy, right? And the derivative, that y is just constant. So I can pull the y out and I just get the x derivative of x, right? And so that just gives me Does that make sense? So it was a direct message for those of you who are wondering what I'm doing. It was just, how do I get the, negative 4y and the negative 4x? Yeah, okay, cool. So kind of coming back down here, we get x, we can difference of squares again. If you go straight to this, great. That's what I had done originally, but I was like, no, I think people are going to be upset that I was able to go straight here and ask me questions. So I just kind of spaced it out. So this has to be equal to 0. And of course, I guess we could factor this into x minus 1, x plus 1, x squared plus 1, x to the 4 plus 1. So that tells us x is 0, 1, and negative 1. The 8th root, where did you want me to take the 8th root?
X to the 8 minus 1, that'll x to the 8 has to.
Oh, I see. So you say
1.
x is not 0 and cancel it out?
Yeah.
Yeah, I suppose you could do that if you want.
You need a factor to be.
Yeah, I mean, you could do that if you want. I think that is okay. But either way, so we get x is 0, 1, and negative 1. Now we need the y value as well, right? So we come back here and we use y equals x cubed. So from y equals x cubed. So we're going to get, if we plug in 0, obviously we get 0. If we plug in -1, we get -1. And if we plug in 1, we get 1. So our points are 0, 0, 1, 1, -1, -1. And that's answer B. Okay, so let me zoom out on that one so you can see it. And then does that make sense? So you see it's a little bit more complicated, right? Like we have to now solve two equations and two unknowns in order to be able to solve this. And you can imagine if this was a function of 3 variables, there would have been 3 equations and 3 unknowns. And again, not linear, so you can't even use a matrix in order to help you solve them. You actually just have to solve them. So the fact that we continuously get these nonlinear equations, nonlinear system of equations, part of what that numeracy question was asking you, right? I gave it to you and I said, try and find all the values x, y, z, and w, which do this for you. And the reason is we're going to be doing that a lot. So you all need to be able to solve such systems, right? And a lot of cases, there isn't like an obvious algorithm for doing it. It really depends on what the system looks like. And you'll just have to find something which works, right? A little bit of practice will help. Now, I was asked to just kind of go back up to the slide 4 answers so it could be seen. So I'll just go up there really quickly before we take up the last question, which we won't have very long for. I don't really have much to do. Maybe, you know what? I don't really have another. We could try this. Let's see what happens. No problem. All right, so let's try this one. This one isn't too big a deal. I just want to see if you can do it. And we'll finish off our day on this one. I won't ask you too many questions related to this, but you should be able to. This is the sort of thing used in order to help you visualize what the graph of this thing looks like, right? So if you want to figure out what the graph of x squared minus 2x plus y squared looks like, and you don't have something like Desmos available to you, the question is, how do you do that? What is this thing? What does the graph look like? And so what you do is you take a bunch of cuts, right? What you do is you say, let's look at almost like an MRI, if any of you guys know how an MRI works. You like say, okay, we're going to take a cut at 0. We're going to take a cut at 1. We're going to take a cut at 2. We're going to take a cut at 3. And we're just going to graph these two-dimensional shapes, and then we're going to, extrapolate, or rather interpolate them together to figure out what the graph looks like. And that's what you would have to do back in the day, before graphing software came about. Math, as much as we think math is hard, imagine if you didn't have computers to help, right? It used to be really bad. It's hard to appreciate how much of a difference it makes. Yeah, they were nuts. Especially, what's crazy to me? There's, and actually I can't remember if we were talking about this in this class, but obviously there's like Leonhard Euler, right? Who is generally renowned, possibly only competing with Gauss as being the greatest mathematician of all time.
I think we did talk about that this semester in this class.
Dude was blind, right? Can you imagine doing math blind? Can you imagine not being able to see the work that you were doing and just doing it all in your head? Like, that's what I'm saying, right? Like, that's how crazy this guy was, is that on top of being able to do it all. And so what he would do, I think, when he would write his papers is he would dictate them to his son, and then his son would write them out. And so that's ultimately how that happened. But pretty much unanimously known to be, he's for sure one of the greatest mathematicians of all time, if not the greatest mathematician of all time, right? When we play with e to the power of x, that e is for Euler, right? Like, that's him. Okay, so we can't go too long because we are approaching the end of class. So I'm actually going to close this really quick here in like 10 seconds or so. And I know some of you maybe are on the verge of it. And if you are, you can just ignore my solution. But I'm going to close it just so we can kind of go through it and talk about it. Okay. So end pool, and we share. Yeah, actually, you know what? Consensus here is on C. C is absolutely the correct answer, if I recall correctly. It is a circle. Okay, so for this question, we have f of xy is x squared minus 2x plus y squared. And we want to look at f of xy equals 3. Right? So 3 is equal to x squared minus 2x. And we want to say, what sort of shape is this? Okay, and what do we do? Does anyone remember how you do this? Actually, I guess I should subtract the 3 for, oh no, it doesn't matter. Plus y. What am I doing? I didn't work it out, but my understanding is that x squared and y squared have higher priorities of 2x, therefore it was essentially, oh, that's an interesting way of doing it, Luke. I mean, but the thing you have to be a little bit careful is that if the number on the, what if it, no, I mean, that's not a terrible way of doing it. You could definitely do it like that. It's definitely going to be some sort of conic section, but you actually could have gotten like a cone out, right? So you do have to be a little bit careful about that. If the numbers worked out perfectly, it could have actually degenerated into a cone. Yeah, exactly, Hasten. I'm completing the square. Right? So if you complete the square, this is a circle centered at 1, 0 with radius 2. Right? So it's a circle. That's a badly drawn circle, but yeah, mine is apparently an egg. I mean, the length on the right is definitely not the same as the length on the left. So this is a very poorly drawn circle, but you get the idea, right? This isn't, as much as Jordan was saying everyone was an artist, that's old school mathematicians. New mathematicians are not an artist in any way, any description of the word. There you go. There's a better circle. That's right, exactly. Okay, so like I said, I don't want you to worry too much about that. There's not going to be there's not going to be too much of this sort of thing. How do you solve this using Desmos? You would here. Let me throw this up on a thing. Desktop. Which desktop do I want? Desktop 2. All right. So here's what you do. Stupid thing. Get off my screen. Thank you. Calculator. It doesn't even connect. What, my drawing?
Yeah, your circle had a bit of a gap.
You're all such critics, right? When it comes down to it. Oh, it didn't connect. Oh, it's not a circle. Also pretentious, so bougie.
I mean, are you surprised coming from myself and Ola's?
Maybe not, right? So Durham, I literally just plugged the equation into Desmos, right? It gave me it. Was that whole thing just to get me to put it in so you could show me what a circle looked like? If so, that was a great troll. That was truly wonderful. There's something else here too. Actually, you know, while we're in Desmos, how do I do the Desmos 3D thing? Let me see if I can. Yeah, let me see if I can give you. What the hell is this D thing? Go away, D thing. Let's see if I can graph this. Not minus 2x plus y squared. All right, this is good. Okay, so this, yeah, no, there's a 3. Okay, so think of this function, right? F of xy equals x squared minus 2x plus y squared. If you wanted to graph this graph occurs in 3 dimensions, right? This is a 3-dimensional graph. And what we did is we just took the cut z is equal to 3 out of it. I don't know if I'm going to be able to add that. Oh, no, that was literally not what I wanted to do. Is okay, good. I wonder if it'll let me add. No, it just has no idea what I'm asking. Oh, maybe let me plot just g of xy equals 3. No, Desmos hates me. Okay, so yeah, I know. It's because it doesn't, it's kind of hard to graph three-dimensional things. Right? Let me see. Ugh. Ugh. No, that's not going to do anything. Okay, so what this is a big bowl. Okay, you know what? Let's try, maybe let's try Wolfram Alpha. Maybe it will plot it better. Was it minus 2x plus y squared? Yeah, for sure. Okay, there you go. Maybe that's a little bit better. Okay, so you see this picture? So it's basically a big bowl, right? It's kind of right now, it's cut into a box, but what you see is it's this big bowl. And yes, it's not a cone though, right? Because a waffle cone, if I think about a waffle cone, it actually kind of comes to a point. This thing is a bowl, right? It has like a soft bottom. And so what we've done is we said we wanted to look at where this function was equal to 3. So we just took a cut of z equals 3 and went shing, and we looked at, you know, what was left over. Like, what did it look like when I cut that piece out? And you can't quite see it because the graph doesn't go high, but you can kind of see it in the contour plots that if you make these cuts, you just get circles, right? I wonder if I can, from z or for z equals 0 to 5. I wonder if that will work. Maybe not. Yes, I know it's an infinite paraboloid, stupid Wolfram. Anyway, you can imagine if you take this bowl and if you cut a bowl and you look at the shape that's left over from the cut, you'll get a circle, right? And so this is kind of the sort of thing we were doing. We said, if you cut it at a height of 3, what do you get? You get this circle. And then you say, okay, if I cut it at a height of 2, what do you get? You get a slightly different circle, right? You get a smaller circle. And then a slightly smaller one. Well, you know what, Olis, though? These aren't even my tools. My tools is I would literally just figure this out and draw it instead of using a computer, right? Sure. But anyway, you guys can figure out how to graph 3D things and make it work for you. But yeah. So that's sort of the idea there, right? And you can use these are called level sets. You can use these level sets to figure out what a thing looks like. So for example, imagine you were trying to figure out what a mountain looked like. Actually, yeah, let's pull up a topographical map. Have I talked to you guys about topographical maps before?
You kind of did one in the video with altitude.
Right, okay. Y, internet, Y. What's one here that looks okay? All right, yeah, let's. Okay, so from this, right, you can look at this and actually you can get a pretty good idea of what the things look like. Even though it's a two-dimensional thing, exactly, you get an idea of where the mountains are, right, and where the valleys are. And a line, any line that is connected, those are all of the same altitude, right? You can see even here, it might be a little bit hard to see, but this is 1,350. This looks like it's American, so that's probably 1,350 feet. And anything along this line has that altitude, right? And so what we were doing, don't they do this in geographic? Yeah, absolutely. So what we were doing is we were computing what the topographical height was at 3. Right? We were saying if you take this big bowl thing and we want to figure out what things occur at height 3, we make that cut and we draw that line, right? And if you draw enough of those lines, you get an idea of what the thing looks like, right? So you can imagine if we had done this for a bunch of different values. Okay, I'll try and draw a better circle because you're all critics, but all right, here's our point. So here's like the line, you know what, I'm gonna move this point over a bit more, like there. Okay, so here's the line 3, right? Here's the thing of altitude 3. And you can imagine if you did the thing with like altitude 1, you'd get something like this, right? And if you did altitude, 10, you might get something like that, right? And so if you think of this as you're looking at it down from above, then you're getting an idea of what the shape of this thing is by looking at its altitude lines, right? Yeah, exactly. Yeah, it's a reverse mountain, right? Yeah, Z equals 3. I just called it Z. You can call it whatever you want. So Olas, what I'm saying is I'm plotting Z equals f of xy, right? So if I want to, I actually might be able to draw this better than graph it, but I mean, that kind of depends on my graphing abilities. So this thing looks like a bowl, but it's centered kind of here. So like that. Right, so yeah, what I'm saying here, when I say Z equals that, I'm saying this is the Z axis right here, right? And maybe this thing right here, that's Z equals 3, right? Here's like Z equals 5 or something. Here's like Z equals 10. And so we're taking these slices. It really is more, it shouldn't tip off. I think a football kind of like comes a little bit more to a point. This is a little bit more smooth. Again, don't take my drawing as somehow a master reflection of it. But what I'm doing is I'm cutting these things into slices. And then if I plot the slices, I can think about what this thing looks like in 2 dimensions without trying to rely on a 3-dimensional rendering, right? And so that's the idea there. That's what we're doing, right? You know what I might be able to do? Let me come back to this computer. Let me see if I can. Let me see if I can do this. So let's go to Desmos again. And let's ask it to do, so x squared minus 2x plus y squared equals c. And then we'll add a slider for c. And I want this to go from 0, and let's say go to 10. Right? So what I'm going to do here is we're going to just, as I change, what I want you to think about is, let's suppose that we're looking at this from above, and what I'm doing is I'm letting the Z plane. Okay, so this is the XY plane, and what I'm doing is I'm taking a bunch of different cuts at different heights, and what the slider is doing is changing the height at which that occurs. And what you can see is it's exactly what it ends up sweeping out. Right? Do you see this? Can you see the shape that it makes? Right? As C becomes higher, as I move the slider to the right, it's getting closer to you, right? So you can see the shape that it makes by me doing this, right? So if we go back to our 3D picture in Wolfram Alpha, why are there dips in the Z value? Here, let me just pull it back up. Is it still up? No, I must have gotten rid of it. So dips in the Z value? What do you mean? So there's definitely a minimum, right? This function actually has a global min, not like dips. Oh, like here, like this kind of parabola thing. So that's just because at some point it's plotting it in, like it's in a rectangle. So if you took a bowl and cut off the edges of it, you would get something that looked like this, right? Think about, you took a nice big wooden bowl and you sawed off the sides so that you could fit it into a rectangle. It would look something like this, but actually it does keep going. It's just that you can see here that it's kind of limited its domain to these edges, right? But it does actually keep going. It's just it hasn't included that as part of the domain. Exactly, yeah, it's the X and Y restrictions on what X and Y can be, right? But it does actually keep going. Right, this is just as well so you can kind of get a look into it. If I restricted X and Y, like you can play around with the dimensions so that it looks it doesn't cut off like that, but I'm not going to worry about figuring out how to do it with Wolfram Alpha. But that's why over here, again, can you kind of see it now? I know you guys were kind of like, oh man, what the hell is this thing? But maybe you can see it a bit more, right? Do you? Yeah, yeah. So there's no axis exactly, but you can see it's a bowl. And again, you get these same sort of dips here, but these dips aren't actually there, right? They're just because we have restrictions on what X and Y can be, right? You can imagine it actually continues onwards and upwards, but you know, it looks like a bowl, right? And so you plot all of these levels and you can get an idea of what this thing looks like. And you can see intrinsically there's actually an issue with kind of visualizing these things. In fact, it gets so much worse. This is a function of 2 variables. But if you think about most of life, life mostly occurs in 3 dimensions. In fact, life mostly occurs in 4 dimensions, right? You have 3 spatial dimensions and 4 dimensions, let alone if you're working with, you know, equations, whether it be in physics or finance or economics, that have potentially dozens of variables, and you just can't graph them anymore because the graphs might occur in 13 dimensions or something like that, right? So you don't have a good idea of, excuse me, what these things should look like anymore, and you kind of have to trust the analysis and the algebra, right? Can you do graphic design by only equations? There are theorems you can prove that basically you can draw anything in the graph just by using it, like anything in the plane just by using equations. And there are people who do it. There's actually a really cool equation, Chifeng, if you want to try it out. There is an equation which graphs itself. So if you actually were to plug it into Desmos, the graph that it renders is its own equation. And it's a cool thing, and I have no idea how anyone came up with it, but it's sort of a weird thing that you can check out, and it's not useful mathematically, but no. So what I'm saying, Olis, is like if you were to graph x squared, the graph shows up as like y equals x squared, right? Like that's what the graph actually looks like, is the equation that defines it. Do you know what I mean? So it's not that y equals x squared is a parabola, it's that it shows up as the equation y equals x squared when you plot it. Right? And that I think is a little bit crazy. Yeah, it literally writes the letters. I'll see if I can find it. So self-describing graph or something like that. Yeah, it's not nice at all, but it definitely is a thing. Oh yeah, here it is. So here, I'll put it in the chat.
Is it the 1/2 less than involving like mods and floor functions?
Yeah, exactly.
That is a good point. Like, I don't understand how the hell anyone came up with this.
Yeah, that's nuts, right? Like, how do you come up with that? Like that's crazy. That's nuts. Right? But it's kind of an interesting little example of people doing some crazy stuff. But if you want, you can go look up at people. I mean, it's not too hard to do, but you can definitely just, I don't know. You try throw it in Desmos, see what happens. But the whole point is that it's not, I think, too continuous. Basically, you would just, it's probably almost easier to plot it by hand, right? And just, you get this nice grid of points and you check, does this point satisfy this relation? Does this point satisfy this relation? It'd be easier to just write a computer program which does it, right? Bonus assignment? I don't think I was talking about a bonus assignment?
You were talking
about the
survey.
Survey
that would give a bonus.
Right, Christine, thank you. Massa, so I think sometime next week, you know, a lot of people were asking for more of those like concept quizzes that we had in the beginning of the year that were worth 1%. And I think mostly just because people want the percent, right? And so what I want to do is I want to throw out a little survey out there just to kind of get an idea of, well, that's great to hear. But what I want to do is I throw out a little survey, which hopefully most of you take seriously, but basically anyone who does it will get 1%. And that will be the thing. Yeah, Jordan's year got 0 bonus points. They didn't get anything. So yeah, that's the idea. Just keep an eye out for it. I'll put it in an announcement. So, it'll show up as an announcement, and just keep an eye, read the announcements. Again, I'm going to aim for sometime next week, and that's when it'll go up. Okay, everyone. Well, anything else? Hopefully that makes sense. Again, if you want to practice partial derivatives, just make something up. No, I don't think we've even started. We'll make it eventually. The final exam for us is due. Where's my calendar? We actually have to have it submitted by the 9th. So for us, it has to be submitted by the last day of classes. And in that time before that, we also have to make a term test. So I don't know. We're going to start working on it probably tomorrow, but it'll take 2 or 3 weeks to actually get through. Yeah, so we're working on it. But exams take a long time to make, right? Yes. Yeah, I'll keep that in mind. Yeah, you guys still have test 8, so right, keep that in mind as well. Okay, so anything else? Otherwise, I think we can comfortably call it a day. I can probably stop recording anyway.